Hello, everyone. Okay. Could you hear my voice? Yeah, thank you.
Yes.
Thank you. Okay. Now it's time for lecture 3. It is our big honor to invite a famous doctor and professor to give us a lecture this evening, and I will introduce him in brief. Dr. Junbo Jia, who was born in Beijing, is currently an expert senior engineer of the world-famous marine engineering company Acar Solutions and a member of the Norwegian Academy of Engineering. He also serves as a member of ISO TC 67 Offshore Structures and invited expert of the European Group, a founding member of the International Ship and Offshore Structural Engineering Conference, a member of the Technical Committee and a director of the International Society for Offshore and Polar Engineering. He has organized and participated in the evaluation, design, modification, and project management of nearly 40 marine structures and nuclear power plants of various technologies in Europe, America, Japan, and Australia. And his topic is dynamics in engineering. Now let's give a warm welcome for Dr. Junbo Jia's lecture. Welcome.
Hello, can you hear me?
Yes.
Okay, thank you so much. It's a pleasure to attend this international summer school on smart city. And there are different fields in the SPRS activities, and civil engineering has a large scope. And I think today I'm going to cover a part that related to civil engineering, especially structural engineering and geotechnical engineering that have some sort of links to the ISPRS work. So I will begin my talk from the basic definition of structural dynamics. Dynamics is concerned with the study of force and their effects on motions. So if you have a system like this, and then you have force, you have stiffness, a system like this will exhibit some sort of like dynamic behavior regardless what type of environment you have, as long as you have a force that have certain frequency close to the frequency of the system. So I will show this in detail in the next few slides. So we also heard about another definition called kinematics, which is only concerned with the motion of objects without reference to its causes. For example, when we study the motions of atoms, we are mainly concerned with their motions rather than the cause of their motions. So it's another field. So the dynamics is actually well recognized a few hundred years ago, but now, even now, we still have a lot of problems that cannot be solved properly due to wrong understanding of the dynamic behavior for structures, for geotechnical issues. So today I'm going to show some of those accidents and to recognize the engineering significance of dynamics. So what's the differences between the dynamic and statics? Because statics, it's very well known because it's simple, and over history, statics are dominated basis, which means for any type of structures or foundations, as long as you have enough strength and stiffness, it's okay. You can resist the external loadings. But when we are going to dynamics, that can be totally different. For example, if you look at this cantilever beam, subject to, you can look at that as either the wind loading or the ocean wave loading, and impact this cantilever beam. And then if you only think about statics, think that this force is statically applied on the structure, you have bending diagram like this. However, if you consider the inertial force from the entire structure, especially from the top mass here, you have a reacting inertial force applied on this cantilever beam. Then you have additional loading like this. So the total dynamic bending moment is essentially a combination of static loading and dynamic loading together. So this is the dynamic bending moment compared to the static bending moment. You will see a significant differences. So if you design your structure based on only static bending moment, that as I mentioned, it's very recognized hundreds of years ago, and then you will have a underestimation of loading, which will result in a unconservative or unsafe design. So the most important characteristics for the dynamics I introduce here is because they're inertial force. Due to the inertial force, it makes dynamics much more complex than the static problem. In addition, dynamics also involves the interaction between the stiffness and mass. So if you look at one structure, that's one of our design for GBS structure with the top side, and we try to investigate under the seismic loading or the earthquake loading, how the dynamic response will vary depending on the change of the stiffness of the cantilever beam. You can think about that. We try to do a parametric study to vary the stiffness of the leg of the cantilever beam supporting the heavy topside structure. You will see we have a reference stiffness, which is noted by the red line. That's their response over time. And we have a less rigid stiffness for the cantilever beam. We call that half leg thickness. And then we have a double leg thickness, which is most stiff structure we have with this triangle. So you will see, if you only think about statics, it's like you don't need to consider any inertial force, then which means if you have force one, for example, you have a displacement one, and then if you double your force, generally you have double displacement as long as it's linear. However, this doesn't apply to dynamics. For example, even for a higher stiffness, like this double leg thickness, this have a higher stiffness for the structure, we have in certain time instant, we have even higher structure response than a reference stiffness or even half of the leg thickness, which means dynamics are very sensitive to the excitation frequency, and also they vary with time. So during the time, they will have a strong interaction between the stiffness and mass. So both characteristics, inertial forces and interaction between the stiffness and mass, makes dynamics quite different from their static counterpart. So I will show this simple structure. By showing this simple structure, I try to illustrate what the essential characteristics of dynamics. If you look at this swing and the rider on the swing, this girl, in order to increase the amplitude of swing, either the rider or her parents, for example, have to excite this swing in phase with the back and forth frequency of the swing. So that's what we call the natural period, which is one time duration for one round trip of the swing. So this, if we look at the dynamic equilibrium, we can easily derive this eigenperiod or the natural period of the swing is only related to the length of this equipment, as long as the swing angle is very small for example, if we have 23 degrees for this angle, between the small angle assumption and the large angle assumption, we only have 1% differences when we determine the natural period. So this law is actually called the law of pendulum, which is found by Galileo when he looked at that the lamp on the Pisa Cathedral back and forth in a constant period at his age of 19. So it's must be a very great observation at that time, because now we feel it's quite natural. We know they back and forth in a constant period. But if you go back 400 years ago, it's must a great mind that can find out this rule. So by introducing the natural period, now I try to illustrate what's the dynamic response in different frequency range. For example, if you have a system, if you look at this system, spring mass system, if you exact this spring mass system very slowly, which means the excitation frequency is quite low compared to the eigenfrequency or the natural frequency of the system, then we call that stiffness controlled domain, which means that the external force or the external dynamic excitation force is encountered purely by the stiffness of the system. But if you go further and push the frequency of excitation a little bit faster, then you actually go to the damping control domain. In this domain, the external force is mainly overcome by the damping force of the system, so the stiffness term becomes smaller. And then if you further go faster to exact the structure, and then you will see that both stiffness term and damping term become invisible, and the external dynamic excitation is mainly overcome by the inertial force or mass-related force, and then they have a balance. This region, we call that mass-controlled region. So both damping controlled region and mass controlled region, which means as long as your excitation force is close or above the natural period, natural frequency of the system, you will have inertial effects, which we call that dynamic domain. So if you look at the response, the bold line is external excitation force, and the slightly slender line is response. You will see if you in the stiffness controlled domain, your actually response follows in phase with external excitation force. But if you exact the structure at their natural frequency or close to the natural frequency, you will see that structural response have approximately 90-degree phase lag with the external excitation force. And if you further increase the dynamic excitation frequency, and you will see actually from this picture, the system will be anti-phase with the external excitation. You will see this black base is external excitation, and this red mass is your system mass, and the system mass is actually moving toward the force, so they're anti-phase. So those characteristics are quite important when we investigate the dynamic behavior of any type of system. It's not only related to civil engineering, but also, for example, mechanical vibrations, and in other things like currently I'm working on a nuclear power plant, and there are a lot of equipment, and even the plant itself, they are quite sensitive to dynamic loading. So we have to observe in which way we can reduce the dynamic response of those sensitive structural components. So we try to avoid resonance, of course, and if there's some frequency quite close to the resonance frequency of the structure, then I have to add additional damping. For example, some external damper in order to make those to fulfill the relevant this IAEA requirement for the nuclear power plant. especially the reactor. They are quite sensitive to vibrations. And it's not only nuclear power plant, it's other type of structure also are sensitive to dynamic loading. Even human being or animals can cause the resonance problem. For example, when a people is walking on a bridge, or for example, the floor of a building, the people walking is like a series of vertical force acting on the floor. If the frequency of the walking is close to the eigenfrequency of the flow, it can cause a problem and for resonance and even the collapse of the entire structure. For traditional bridge structure, some structure have a quite close frequency to the people's natural excitation frequency, and they can have strong vibration problems. So I showed here 3 examples. Of course, there are much more, but I try to illustrate the seriousness of the people's excitation loads. For example, when 150, 60 years, 70 years ago, in Angers Bridge in France, when around 500 people walking on a bridge, it's a suspension bridge, and they are ordered to break their steps in order to avoid vertical resonance of the people's excitation to the bridge. But essentially, when the bridge is swing horizontally, they also have a horizontal excitation to the bridge. And this horizontal excitation actually is the cause of the resonance of the bridge. Because when you are working on a very flexible bridge structure, for example, like this, and then you try to make the balance between the bridge and your body, try to make a balance, then you inevitably try to exact the structure horizontally. If the structure's horizontal vibration frequency is quite low, for example, below 1.5 hertz, you may actually exact the structure to resonance. This accident actually causing around 250 soldiers fatality in this accident. So it's half of the soldiers that got killed. And it's not particularly French people who suffered from those type of accidents. In Britain, there are also similar thing. And when around 200 plus soldiers working on a cast iron suspension bridge, even older than this Angers Bridge in UK, and they also do the similar thing and try to exact horizontal excitation, and finally causing the problem of the resonance and collapse of the entire bridge structure. So now people understand that it's not a vertical excitation can causing the problem of resonance. It's also horizontal one. But even nowadays, we still have similar problem like this Millennium Bridge, which is finished construction in 2000 in UK. This is Thames River. And after its completion, we also see significant horizontal vibrations on this bridge. So they have to stop the service after that and implement a lot of damping devices and also the mass damper, different viscoelastic and viscous damper on the bridge in order to reduce the vibration. That's actually not foreseen when they are designing this pedestrian bridge. So that's a human vibration can causing the problem. More closely to our life, the vibration of the piping can also have a lot of problems that can cause dramatic increase of fatigue damage on the connection of the piping, because when the flow is going through the piping, the flow itself is similar like a human body to exact the piping. So when the piping's excitation frequency is close to the piping's natural frequency, it can cause the problem of accumulate resonance vibration that can cause the fatigue problems And then you will see that there are different mitigation measures, like you can have some material to absorb the vibration or isolate the vibration, or even you can redesign the streamline. For example, this sharp bending, we can do like more soft bending to avoid excessive vibrations. Actually, those piping vibration is significant with regard to especially the industry infrastructure. We have many problems due to the piping vibration we are treating every day. And if you see this picture, you may wonder what's the cause of this. And it looks like it's after earthquake, and then some buildings just get collapsed. Some dropped objects just fall down to the ground. And actually, I can tell you this is not due to the earthquake. It's due to a North Sea storm that occurred some years back. This is a picture we have to show the office room that involves our platforms. And this is another platform in the actually in the archive room. So if you think it can resemble after earthquake scenario, as far as I know, that the majority of fatality due to earthquake is not due to the collapse of the structure, it's due to the dropped objects. So this scenario, even it's not due to the earthquake, it can cause the similar fatality if the structure is not properly designed. The dropped objects can kill people and causing other damages. So this is due to some sort of like dynamic design that we have to treat carefully. So when we talk about earthquake, I want to go further to this geotechnical engineering to show the dynamic things are heavily involved in our earthquake design. Let's go to first Mexico City earthquake during 1985. The moment magnitude of 8.1 earthquake hit a place almost 400 kilometers away from the Mexico City. But in the Mexico City, there's still more than 400 buildings collapsed. Another 324 buildings got seriously damaged. After a forensic study after the earthquake, it's found that the majority of those buildings are ranged from 8 to 18 stories high. If you can have some similar or very simple formula to correlate the eigen period or the natural period of those buildings have typically a range period, natural period between 2 to 3 seconds. And then we try to see the geotechnical conditions. The Mexico City is built above the soft clay layers formed from an ancient lake deposits with 37 meters high thickness of those soft clay layer between 37 meter to 57 meter thick. And we know that similar like our structures, the soil actually is rigidity or the stiffness heavily related to their shear stiffness, which can be determined or correlated to the shear velocity. The shear velocity for the soft clay in the Mexico City is around 75 meters per second. Then we can use a simple formula to see what the resonance period of the geotechnical soil foundation. And then we can use this formula 4 times of the soft clay layer thickness divided by the shear velocity of 75 meters per second. Then we got around between different thickness, we got around 2 seconds to 3 seconds, which is exactly the natural period of our building. So we can identify those that dynamic resonance is an important contributing factor to the collapse of both building and also those damaged buildings. And I try to use this picture. This is one of our project, try to show in that how significant the soil itself can amplify the seismic motion. And you know this is also like bedrock, and fracture occurred at the bedrock level, and then they go through the soil layers. The soil layer will work as a filter to amplify some frequency of soil response and de-amplify some other frequency response. So if you see that this is one of the earthquake on the bedrock due to the fault rupture, maximal acceleration is only 0.1 gravity of acceleration. And then due to the filter effects of soil layer, is similar like the filter effects of the soft clay. After this 17 soil layers filter effect on the ground surface, the acceleration, the peak acceleration is almost doubled. So you will see how significant the soil itself can work as a dynamic amplifier to increase the ground motions. So in order to decrease the dynamic response on the protected structure or the top structures, one way to do that is we try to cut the transmission path between the soil or the foundation and upper structure. One way to use to do that is we try to implement a so-called base isolation. Is we try to put some soft connection between the top structure and the soil foundation. And then when the seismic motion is transmitted through the foundation to the top, because this soft layer, the dynamic demand is reduced significantly. So this is without isolation. You will see a large deformation of, for example, if you are thinking about a high-risk building, you will see a large deformation of this structure from the interface between the soil and the top structure to the top of the structure. But if you use this soft layer isolation, you will see a significant decrease of the response. So another way we try to decrease the dynamic response is we try to add a secondary spring mass system. So by tuning the secondary mass spring system, which is much smaller but have a almost identical eigenfrequency to your main structure. When the main structure has sort of like dynamic resonance, their energy will be transferred very smoothly or efficiently to the secondary mass spring system. And then finally, because energy transfer from the main structure will have a much less vibration than if without this secondary system. So you will see, this is the middle picture. You will see that when I tune the secondary mass spring system close to the mass spring system of the protected or the main structure, you will see the main structure, if you tune very carefully and have a certain high ratio of smaller mass compared to the main structure's mass, you can almost make the main structure have very minor vibrations. This we call that dynamic absorber, and we have seen extensive application in our engineering world. I show one example is this Millennium Bridge in UK, in London. As I mentioned, due to the human beings' vibration excitation, there is excessive resonance vibration on this bridge. So after the closing of this bridge, we call that tuned mass damper, which is a type of dynamic absorber. It looks like that. They put the mass and spring and also some damping in this system and put underneath the bridge deck. And then when they tune the eigenfrequency of this system very close to the bridge deck's vibrations, they try to actually eliminate the excessive vibration of the bridge. This is designed by a German company called GERB, and you will see that the decrease of the dynamic response is quite significant due to the implementation of the PMD system or the dynamic absorber. And this is even more famous one is Taipei 101 building. And I believe many of you see some relevant movies from that. They also try to put a spring mass system. So what the spring looks like is actually similar like the swing I talked in the first few slides. It's by tuning the length of the hanging part of the swing. They try to tune the entire mass, this sphere system, quite close to the eigenperiod of the building. This building have 101 stories. So this secondary mass spring system have a period very close to the 6.8 second, which is the protected structure's eigenperiod. And then when the wind, especially the wind comes, this secondary system, and even I call that secondary, you see the mass is quite heavy, it's weighted 660 tons. And then they try to absorb efficiently the energy from the main structure so that the entire structure's response will be reduced dramatically. Another phenomenon also occurred, which is related to dynamics. For example, we may heard about this vortex-induced vibration problems in many engineering failures. For example, this is one of our engineering problems we received from our customer, and it's due to, for example, you have a member, and when any type of flow, either it's seawater or it's wind go through a rigid or maybe flexible structure components, and due to the regular vortex shielding in the wake part of the flow, they will have a excitation perpendicular to the flow direction, which means if your flow direction is in this direction, the vortex-induced vibration, cross-flow vibration problem will exact the structure in the vertical direction that is perpendicular to the flow direction. If this vertical excitation due to the vortex shielding is close to your structure's natural period or the structure component's natural period, it will cause resonance problems. And with resonance vibration accumulated, they may cause structure fatigue problem. This is a real engineering example. The top part of some members got cracks, and they have a potential to actually collapse down that can cause fatality even for the entire platforms. So actually, this have been observed in many laboratory tests, but in North Sea, we still see that even surf vibration have been reported on several high-risk flare booms in North Sea. The actual vibration amplitude was up to 20 times higher than the one we measured in the laboratory test. Excuse me. So I try to show one example. This is actually a recent topic that arose in China. It's a high-risk building called Saiger skyscraper in Shenzhen in south part of China. The height is around 300 meters without this mast, I mean the height. And they have a natural frequency of 0.17 hertz, which let's say is around 6 seconds. If we think about vortex shielding, the building itself can avoid vortex shielding quite well. However, in May this year, noticeable vibration with maximum amplitude at different floor have been observed for this building at a frequency of 2.1 hertz rather than 0.17 hertz, which means that actually there's some loading except the higher order vibration of the entire building. So by a forensic investigation team, which comprised several expert group members, they found out that because of the vortex shielding problems that exact the vibration of the mass on the top of this building, at around 2 Hz in the wind speed around actually 12 meters per second, the vortex-induced vibration of those masts actually worked as excitation force that actually causing very high order vibration modes to occur for this entire building. So you will see this building have a very noticeable vibration that may not causing any problem for the safety of the building, but it may cause a problem for the actually comfortability and serviceability of the building. So the conclusion is the vortex-induced vibration of the mass resonance actually triggers the building's false mode vibration. And due to the eccentricity of the mass, you will see the mass is not in the center of the horizontal plane of the building. They're on the side. So they're also causing some torsional excitation. So both the bending of the building due to the excitation from the vortex induced resonance vibration of the mass together with the torsional excitation, it causing a sort of like higher order resonance problem for the entire building. So when you go to study some structural dynamics, you will see the mode shape. That's you have first fundamental mode shape, and then you have also higher order of different frequency mode shape. This is close to the sets force 1, 2, 3, 4, the force vibration modes that causing this problem. So this can be actually identified through some numerical simulation. For example, you can actually using the dedicated CFD, computational fluid dynamic method to compute the vortex-induced vibration to predict potential problem with regard to that. And you can have some mitigation measures. For example, you see some chimney on the top, they use spiral spikes that actually some people may think they try to strengthen this chimney. Essentially, it's not. They're trying to disturb the vortex shielding so that the excitation frequency will be varied from time to time, so that they will not cause the resonance problem anymore. Or we add some local mass to try to tune the dynamic behavior of those members. This is on one of our offshore projects. So that resonance problem will not occur either. Then in the deep sea, if there is a vortex-induced vibration due to some coming flow, and we also can try to implement this spiral wire to try to mitigate the vortex-induced vibrations. And if you try to look at some buildings, they, from architecture point of view, they may have their aesthetic opinion about designing the building, but actually this also helps to have some roughness on the structure so that this can also disturb the vortex shielding problems in the wake area, that the resonance will not occur due to the vortex-induced vibrations. So different mitigation measures. In the engineering world, we also try to avoid dynamic loading. This is actually most effective if you can do that. For example, in Norway, there are a lot of field crossing bridges, and they have different concepts. One of the concepts that engineering proposed is actually try to submerge your bridge structure entirely into the water. Because on the water surface, there are different wind loading and also wave loading that can cause a different dynamic problem, especially for very slender structure. But if you submerge your bridge structure as a sealed tunnel, then those loading are not significant anymore. Then you can avoid a lot of different dynamic sources. Sloshing, for example, you see this, and this is perhaps on a tank in a track. It's actually due to a contained water, and that if your excitation can excite the vibration resonance of the water itself, it can also causing the resonance problem. For example, this picture is taken by a friend from Germany. He actually showing that if you exact this cup of red wine in certain frequency, you can actually cause excessive sloshing problems. This looks very nice, but in the engineering world, if you have these problems, you may cause a lot of problems. For example, this is some damage scenario due to different earthquakes, like the damage of the tanks and the elephant foot, which means when the sloshing occurs, there are also some bottom rigid mass vibration problems that causing excessive bending moment of the entire tank that can cause a problem of structure failure. In case that your content in the tank is toxic or can trigger the fire, you may even cause a dramatic increase of the fatalities. For example, this is one of the scenario of fire due to an earthquake in Japan, that actually the structural damage is not that high, but because of the fire, it causes excessive cost for the damage. And nowadays we know that those sloshing problem can be analyzed either through some numerical method like computational fluid dynamics, as I mentioned, or through some even simple mass spring system like our dynamic system to actually model different level of water to try to simulate the behavior of those sloshing problems. Dynamics also requires a lot of different type of testing. For example, this is a wind tunnel test we have for one of our floating offshore platforms. We try to use different wind speed, try to see the drag factor or the wind loading on the topside structure in different directions. So if you see this is a base and try to rotate the base to simulate different direction of wind. And also you see this we call drought. And drought is actually the height submerged into the water. Because the different operation conditions, we have different drought. So we have different wind force parameter to investigate that's directly used in our engineering design. Except wind tunnel, we also try to see what the wave loading can cause in the dynamic problems. And this is one of the ship basin tests to see the slamming wave on the platforms. And except the experiment, we have numerical calculation. For example, this is one of our project using the computational fluid dynamics to see the moved semi-submersible platform, how they interact with waves, and we try to fully utilize this numerical model to correlate to the experiments and further use for our design. It's not only the wave itself. You see there are some high nonlinear impacting loads on the structure. And this is actually one of the correlation between the numerical computation and model testing in the ship basin. We see a very close match between each other. So, which means in the future, we can actually very much rely on our numerical model to do the optimization for the designing of this floating vessel. So this is one of the, if you still remember, I introduced some vortex-induced vibration resonance problems because experiments you can do some numbers, but the essential thing is you try to use experimental data to validate your computational model so that in the future design, you can heavily rely on your computational model. That's the way we used for our daily engineering design. So this is one of our design, try to see a submerged piping, we call that technically raster system, how they interact with the subsea current and waves. So you will see the simulation, and they show actually some resonance vibration. If you see this red line, after some cycle of wave and current loading, they try to increase their amplitude dramatically due to the resonance vibration. So that's where causing the problem for our subsea raster design, and we have to treat that very, very carefully. And we also use experiments for earthquake engineering. For example, this is one of the tripod structure. We use that for actually that's one of the experiments movie I borrowed in the BUCA's shaking table test. So you will see that under certain earthquake scenario, the structure's response will be shown in this movie. And also, if you try to look at the foundation of the soil, because the soil have overburden pressure due to the upper surface soil weight and the weight of the upper foundation and structure, we try to actually use this, we call that the eccentric shaking table test. And by rotating this arm, you actually apply the eccentric force on the structure and also on the soil inside this shaking table base. And then the soil's pressure will be simulated using some type of similarity equivalent method. And then you can mimic the overburden pressure of the foundation soil. And then you do your shaking table test inside this small container. And finally, I try to summarize. We illustrate all those dynamics and how we should treat the dynamics. So I call that essentials of dynamic analysis. Is actually to solve the equations of equilibrium. If you look at this one, and the dynamic equilibrium include both the stiffness and also both the stiffness damping, as well as the mass, which is an essential part of the dynamics. We call that inertia. Fortunately, our ancestors, those great scientists like Galileo, Isaac Newton, Rayleigh, and Hooke, already gave a very dedicated description of how we should treat those mass, damping, and stiffness related system. And in nowadays, we also have more challenges regarding to, especially from the last century, mid of last century, we have a large scale structure design which have excessive or a large degree of freedom. So in space, we try to use mainly finite element methods to try to disassemble the mass, damping, stiffness, and force into a single degree of freedom, and then we reassemble each degree of freedom together and to solve the entire degree of freedom system equation like this. And in time, we try to use finite differences method to actually make the time stepping to solve the response in time domain. And in nonlinearity means the stiffness is not constant with regard to the varied loading and deformation. So when your response is changing, the stiffness may change also. So this is not a linear equation anymore. So we try to use, we call that Newton method, or some books called Newton-Raphson method, try to make a linearized iteration method to make a simulation of nonlinearities. So the essential problem is try to solve the dynamic equilibrium of this equation. If you think about static, I just try to mention here, is actually a first order equation, differential first order equation here. So you don't have the inertia and the damping, but when you go to the dynamics, you actually have inertia and damping. Then the equilibrium equation become a secondary order differential equation. So the solving of this problem is much more complicated than a linear first order equation. So we try to use this three way of solving that. So today I'm just very briefly introduce dynamics in our engineering world and how we should treat them numerically. This will be very helpful in the daily engineering design. So I thank you for ISPRS again for the invitation to give this presentation, and hope everyone in the future can notice the significance of dynamics. Thank you so much.
Okay, thank you very much for Dr.
Thank you.
Zhu's wonderful lecture. I think this lecture is on the base of some fundamental concepts and explain the dynamics in engineering with straightaway language and take some vivid examples. And I think it is attractive, rich, and wonderful. Thanks again. And I think some students might have some questions to ask. If you have any question on this lecture, I think you can put down your question on the Q&A board. Okay.
Yeah, there's one question about Dr. Yunmo Jia. Thank you for a very informative lecture. You spoke about the impact of vibration and resonance on pedestrian bridges. I'm wondering if there are similar problems related to the railway or road bridges. What are the possible solutions? You're right that in the railway and also the road bridges, the vehicle itself can also exit the bridge. There are actually a special subject called vehicle structure interaction that has been studied by many researchers. The essentials is to actually investigate the interaction between the bridge structure and the top moving vehicles. Because when the vehicle is moving on the bridge deck, for example, if you have a lorry or truck moving on a road bridge, because the road stiffness and also the truck vibration itself, actually you can exact bridge to the resonance. So the roughness of the road can be a very important parameter to check if your bridge can be exact, and also the speed of the running vehicle. For example, if it's a lorry, if you drive very fast compared to if you drive very slow, you have different type of dynamic loading. One loading may have no problem, and the other loading may causing the resonance problems. And actually, in current days, most of the design codes in the national level, international, such as Eurocodes, I believe many of you know that, they have dedicated description and requirement to avoid different type of vehicle exact resonance problem. As long as you follow the design, it should be quite safe. And also, I try to mention for the railway bridge, it may be a little bit more complicated because the railway track itself is also intermediate dynamic structure that can transmit the bridge, transmits the vibration from the wagon of the railway wagon to the supporting bridge structure. So there are more complicated problems to investigate. There are a lot of research articles, design practice to show how you can reach a very safe design. So second question is how to avoid sloshing trust. Actually, there are very cheap way of doing that is the vortex-induced vibration is caused by a resonance problem. You can definitely allow the vortex excitation, but you don't allow them to causing any resonance problem. So you can do some very simple way to make some, we call that spiral plates, very simple one. We do that actually on many chimneys offshore and also online in factories. We have a lot of engineering practice at our company. We do that very cheaply but can solve the problem very efficiently to use this way. And also you can actually, if you don't want to install those spiral specks, you can actually, because those spiral specks can cause increase wind drag or some hydrodynamic problems due to the increased wind loading or the drag wave loading. You can actually add some damper. What I just mentioned is this dynamic absorber. There are also many different applications. You can add those dynamic absorber purely to reduce the vortex-induced resonance vibration on your structure. That's, you can see many examples in both engineering world, and also there are some research article describing that. So hope those questions are answered properly, or if you have more questions.
Okay. Okay, I think because of the time limitation, we have to finish this wonderful lecture. And let's thanks again for Dr. Junbo Jia's lecture.
Thank you so much.
Okay, bye-bye.
Bye-bye.
Okay, Mr. Jingbo. Mr. Jingbo.
Yes, yes.
Okay, please make some screen sharing, I think.
Okay. Hello, everyone. Our next session will start at 9 p.m. in Beijing time. And now we have about 5 minutes left, and we can have a short break for the next lecture. In the next lecture, we will start the lecture about the situational awareness in smart city by Dr. Shi Shuoxu. Okay, now it's 9 p.m. Okay, hello everyone. In this session, Dr. Shishuo Xu will give us a lecture about sensing and detecting small-scale events from geosocial media data, aiding situational awareness in smart cities. Dr. Shishuo Xu receives her PhD degree in geomatics engineering from Ryerson University in 2020, and since then, she has been an assistant professor in the School of Geomatics and Urban Spatial Informatics, Beijing University of Civil Engineering and Architecture. Her current research interests include geospatial data analysis, event detection using geosocial media data, and urban dynamics and smart cities. Okay, welcome, Dr. Shishuo Xu. Welcome.
Thanks, Jinbo. So will I share my screen or?
Yes. Now you can start. Yeah.
Sure, thank you.
You're welcome.
Sorry. Okay. So good morning. Good morning, afternoon, and evening, everyone. I'm Shishuo Xu from Beijing University of Civil Engineering and Architecture. Thanks RSPRS and BOCA for organizing this virtual summer school. It's my honor and a pleasure to be here to having this university opportunity to give a presentation with you. So today my topic is around geosocial media data and smart cities. It's about geosocial media-based situational awareness in smart cities. I will first briefly give you an introduction to myself and related to today's topic. So what is smart city and what types of researches have been done using the social media data? And finally, I will briefly introduce my own research on spatial temporal event detection using the geosocial media data. I got my PhD degree from the Department of Civil Engineering at Ryerson University last January. And after that, I joined BOCA around last September through the Beijing Overseas Talents Youth Program. And my research mainly focused on the geosocial media analysis, spatial temporal event detection, using geosocial media data and analyzing urban dynamics and smart cities. As one perspective of today's topic, smart city. So what is smart city? What composes smart city? And are there any distinctive features of smart cities? Because there are many different definitions of smart city. Here, we mainly focus on 3 of them that are widely acknowledged. The first one is from the IBM company. It defines smart city as a city is an interconnected systems of systems, a dynamic work in progress with progress as its watchword, a tripod infrastructure operations people that relies on strong support for and among each of its pillars to become a smarter city for all. And according to MIT, they describe cities systems of systems. This one is similar to the IBM one, and they also mentioned that there are emerging opportunities to introduce digital nervous systems, intelligent responsiveness, and optimization at every level of system integration, from the individual devices to buildings and to complete cities and even the urban regions. And the third concept is defined by the Forrester Research Institute. They define the smart city as the use of smart computing technologies to make the critical infrastructure components and the services of a city more intelligent, interconnected, and efficient. Okay, let's stop here. Some students may get lost due to the long sentences and the description of the smart city concept. So let's watch a short video to have a better understanding of what is smart city. Here we go. Okay, from the video, we may find a smart city model. And this model is mainly composed by three major components, namely economic component, environmental component, and social component. So regarding the economic component, it mainly includes public administration and economic actors. And it mainly covers the governance models, urban regeneration, open data, big data, mobility, cloud computing, security, business intelligence, and so on. The second component, it comes from the environment. So it mainly includes the resources and the managerial infrastructures. And for this component, it covers like the environmental actors, including the water, air, energy, and waste. And the third component comes from the social science. It's called social component. It is mainly composed by the citizens and covering our community life, urban mediation, social innovation, human skill cities, civic participation, and so on. So from this model, they are in balance with the sustainable development of the city. This balance is very necessary since we need to create an innovative, prosperous, and civic city for our daily life. Because smart cities use digital technology to improve our day-to-day lives. And in order to help local government pull off this challenge, a comprehensive range of digital solutions, namely urban systems, have been developed, such as the Urban Pulse, a dashboard named Urban Board, and Urbanomics. This covers the citizens, technicians, and government perspectives. In the following, we will have a look at for 3 short videos introducing the 3 urban systems respectively. The first one is called Urban Pulse. It's like this smart application has instant access at all times to the information provided by the project partners. So they can find out about events, services, and layer activities. As residents, we can get involved by sharing information about private parking spaces, riding sharing experience, and so on. So Urban Pulse puts citizens at the heart of a new urban environment. This plays an active role in their own comfort and help the urban environment to operate efficiently and protect the sustainability. The second urban system is a dashboard. So this dashboard is mainly serves the government. So it brings together the technical information and the social network flows with the same goal to put the performance of urban services into perspective and link them to residents' impressions in 4 areas, including the mobility, security, cleanliness, and the environment. For this dashboard system, the data is also provided by the project partners. So let's have a look at of this urban system. The third one is called the Urbanistics. This system mainly serves the technicians, and it mainly aimed at the data analysis. So this system can help the government to better manage the city and to enhance service performance and to help detect events in a more real-time manner. Based on the 3 short videos, we made a brief summary. Are there any distinctive features that a smart city holds and make it different from the traditional cities? Yeah, the answer is definitely yes. So it mainly holds these 4 features. The first one is services to citizens. Cause in smart cities, it aims to deliver better services to citizens, to give them real-time information that may help them to make good choices and contributes to the sustainable development of smart cities. And the second feature is from the citizen participation. Since people live more and more in cities, and they wanted to participate in the debates and to be considered and listened by the decision makers. And they also wanted to be the actors of changes, and they wanted to be as much as decision makers or businessmen. So information and communication technologies enable access to information, and it provides the potential to enable the citizens to play a new and more active role in the city. The third one is about the open feature. It means the open government, transparency, and confidence. The open data and access to the information are very essential in the smart cities. And the information and the communication technologies with the aim to enhance the communications and the interactions between the citizens and the public administrations more efficient. The third one is about the environment. It means the efficient and sustainable management. This is because the development of a smart city is not possible without a strong environmental component. So these are the smart city features. And another perspective of our topic is about the social media. In the past years, are there any researches that use social media data to conduct researches in the urban environment? So as the information technology emerges, it generates a huge amount of multiple types of data, which we usually call them big data. And social media is a typical type of big data. In recent years, a variety of researchers have adopted social media data for their research. And the figure shows the evolution of the big data sources and the technologies, and when the rise of social media data appears. The evolving data landscape over the past few decades demonstrates the increasing availability of location-based social, infrastructure, and biophysical data. So the data availability is the key to tracking progress on the global scale for the city's sustainable development, and even in the region or in the urban scale for proposed sustainable plans. This requires the high resolution data both in space and time. It means it has the high resolution data in both spatially and temporally are very necessary for developing the smart cities. There are a number of social media platforms that are very popular among the world, and they appeal to a huge amount of users, especially the young generation. The Facebook may be the most well-known one, is the biggest social media around the world, with more than 2 billion people using it every month. So that's almost a third of the world's population. This application is very easy to get a start because almost all content format works great on Facebook, including the text format, images, videos, live videos, and stories. YouTube is a video platform where users watch 1 billion of videos every day. It allows users to subscribe or just view, like, comment, or share the videos. The third one is Twitter. Twitter is like a social media site for news, entertainment, sports, and so on. What makes Twitter different from other social media platforms is that it has a strong emphasis on real-time manner. It means the things that are happening right now. So another unique characteristics of Twitter is that the word limits. It only allows around 280 characters in a tweet. This is different from the other social media sites, which may have a much higher limit. And Weibo is similar to Twitter. It's a Chinese version. So it has features similar to Twitter, such as word limits, and it allows users to upload photos, videos, comment, and verification of accounts. WeChat first grew from a messaging application, just like the WhatsApp. It now is grown into an all-in-one platform. Besides messaging and calling, users can use WeChat to shop online and make payment offline, transfer money, book taxis, and so on. So we can say WeChat may be the most popular application in China now. So like places where social media sites like the Facebook and Twitters are not permitted in like some parts of Asia, WeChat may be a good choice. Another one is the Instagram. It's a photo sharing social media site. It allows users to share a wide range of photos, videos, stories, and videos. LinkedIn is well known for the job search. However, it has become a place for the business to establish their thought leadership in their industry and attract talents to their company. Similar to WeChat, or QQ is the top social media platform in China before the WeChat. So it's very popular, and it can be used in around 80 countries all over the world. And they can be used in different languages. It allows users, despite the messaging or calling, it also allows users to play online games, shop online, or make payment. TikTok, also known as Douyin in China, is a rising music video social network. It was the world's most downloaded app in 2018. And users can record videos no more than 60 seconds. They can also edit the video and add music and special efforts to the videos. As we introduced a number of social media platforms, some of them are cost-free to obtain by their provided application interfaces. And they can provide real-time and abundant text, image, and video information. Here, we specify the geosocial media data as if they are geotagged with GPS coordinates, or they are geotagged with place names. We call such social media data as geosocial media data. As the information and the communication technology develops, the Internet of Things and the urban geolocated data, namely the geosocial media data, have been used to expand our understanding, not only of where people are, what they do, but also what they value. So based on the geosocial metadata, what can be done in smart cities? Most evidence points to the promise of geosocial metadata for addressing key questions in 5 domains, including the environmental sustainability that are shown in green, public health in orange color, and the social equity in violet color, and the mobilities, the questions in blue, and economic development that are shown in red. So the large scale publicly available social metadata on people how to navigate and respond to natural landscapes allows the investigate the human-environmental relationships in both greater and smaller scales. The first domain refers to the environmental sustainability. It measures the human-environmental relationships. The social metadata can help researchers to assess the value people place on nature and capture non-material benefits, such as the spiritual enrichment, and a combination of geolocated tests and pictures. The social media, the geosocial metadata can enable the measurement of green spaces popularity and visitation drivers across city at both regional and international scales. Furthermore, the analysis of social metadata during extreme weather events, such as the natural disasters, can support dealing with climate changes and developing disaster response models. Let's look at some case studies using the geosocial metadata for the environmental sustainabilities. The first one is from they did a case study in New York, United States. The Twitter and Flickr data were collected to develop rapid indicators to identify the park access and visitation in urban areas. The climate change adaptation and disaster risk reduction is another emerging field of social metadata-based area. So it incorporates the participatory sensing data, like the Twitter data, with the ground-based sensors, the physical sensors that are installed along the roads or along the buildings. As shown in this figure, we see that the incorporation of the tweets, the Twitter data, can significantly change the resolution accuracy for the local area analysis. This finding would be very valuable for using the Twitter or any other social media data to analyze the climate changes at a global scale. Another one is from the capturing public sentiment and the perception of climate change. Sustainability research where the social media data can help social scientists to make progress. So the sentiment analysis using big data, this is from the Chinese Twitter named Weibo, so has revealed a possible disconnect between the perception of climate change as a global issue and its local implications. Moreover, the social media data can also monitor the social activities during the natural disasters like the earthquakes, wildfires, and rainstorms. Another research is focused on the social spatial interactions between the number of hurricanes related tweets and the spatial distribution. This research can throw light on the large spatial patterns of social activities. Another research domain concerning the situational awareness in smart cities is public health. So the social media data reveal how people feel, move, and make choices in space. So the content and the location of activities can throw light on how the built environment affects health food choices and physical activities. It illustrates where the highest instance of depression and maybe alcohol problems among the urban areas. The Twitter data was used to map the prevalence of unhealthy food outlets in the United States. And also the Twitter data was widely used to explore the extent to which food environments have an influence on the food choices. Also in the United States, they investigate the number of posted tweets, the correlation between the number of posted tweets and the obesity rate in the United States. Another research is concerning the alcohol problem. They investigate the relationship between the alcohol-related tweets and alcohol-related emergency visits. Similar to the correlation analysis, the place and the happiness based on the Spursy words found in tweets were visualized at the map to illustrate the spatial distribution of the related tweets content. Clustering, like the spatial clustering methods were also used to cluster. This is a little different, because this one, they don't cluster the Twitter content, they cluster the users, and they investigate the users' feelings associated with the clinic depression. For the public health, another research is concerning the uncovering the geographical distribution of happiness scores using the Twitter data collected in New York City. And in Australia, the physical activity patterns of mothers of primary school aged children were analyzed using the geosocial media data collected. The third research domain is about the social equity. In this research domain, they mainly focus on revealing how social access to urban amenities play out in space and time and change over varying from the time, and to uncover how boundaries of social spatial segregation are socially constructed, and to indicate why the spatial contours of social, economic, and ethnic divides may be less fixed than that is commonly thought. This is a case study conducted in US. They examine the social spatial division between East and West neighborhoods. Here is a visualization result, visualizing the spatial distribution of different ethnic groups in London, UK. And the fourth square is a picture sharing platform. And this type of social media data can be used to predict neighborhood deprivation. The third research domain is about the urban mobility. The urban mobility is about how people move and they present different patterns in the urban or rural areas. Here is a research, and they focus on developing an agent-based model of urban activity patterns, such as the home pattern, work pattern, eating or shopping. This research will also use the Twitter data. Another one is investigate the correlation between the transit pattern and the public transit pattern and the urban infrastructure. Similar to the first research, this one abstract the crowd mobility patterns and determine how they shape different functional zones at different hours in the New York. Here, this is one visualization result, and they visualize the international mobility flows between countries, between different countries. Also, at a global scale, they use Flickr photos to capture the mobility flows in New York and Rome. The last research domain is about the economic development. So they did a research to identify the most successful urban plazas in the Spain. From the economic perspective, they use the Twitter data to assess where tourists are and what attractions and events they found most appealing and they most talk about. This one they use Dianping data that we are very familiar with to identify the popular restaurants destinations in the city of Hangzhou in China. The shopping flows can also be analyzed using the Twitter. Called the Twitter data, they have the network feature, so they can be used to capture the mobility flows. Although many efforts have been done for the situational awareness research in smart cities using the geosocial media data, but there are still many challenges. The first one is about the population, because some of the geosocial media sites are not universal or are not available globally, and the users of the social media sites are most young generation. So it presents a bias for like the age, like the gender. So it may be considered not to be representative for the sample populations. Another one is about the location, because due to the privacy concerns, some people don't turn on their GPS. The GPS is not enabled. So the geosocial media data, it means a small percentage of the geosocial media data are geotagged. Most of them are not always coordinates or place names. And some people may manually label the locations, but if they manually labeled, there may exist the accuracy problem about the location accuracy. And due to the characteristics of events and places, some of them may be not suitable for macroblogging. Another one is about the sentiment. So the majority of the statements are regarded as neutral. So this one may hinders the abstraction like positive or negative sentiment. Similar to the location, the spatial perspective, another concern is from the temporal perspective. So if we use different time frame, we may get a different data or different amount of data. And like if we do different researches or used for different applications, they may hold different temporal features, like some are weekly events, some are seasonal events. So this may hold different characteristics. Another one is about the privacy problem. It's called ethics. So if we collect the user data from multiple sites or sharing the data with the third parties, some users may be concerned about their privacy. Another one is from the data analysis problem, a data analysis challenge, because the social media data is a huge amount of. So how to analyze the massive networked and unstructured data is a big challenge for the data analysis. Finally, I will quickly go through my PhD research regarding the spatial temporal event detection using the geosocial media data, mainly from the Twitter data. So what are events? I define the spatial temporal events are defined as involving interactive human movements where abnormal patterns emerge in a small area during a limited time. So here I mainly used the Twitter data, and I did detect two types of spatial temporal events. The first type is about the abrupt patterns, and the second type is about the concentration of similar posts. The social events and the traffic events are the representative type of events of these two types. So for the first type, social event detection, I mainly detect the social events using the Twitter data from the spatial, temporal, and thematic perspectives. The Twitter data were collected through their provided streaming APIs, and they were collected in Toronto, Canada. First, the Twitter data was pre-processed, and the outlier data were detected using a distance method. After the outliers were detected, called the Twitter data hold test messages. Then the content were analyzed using a topic modeling method. After their content analyzed, the spatially closed and thematically similar tweets were clustered to identify the social event. Here is a spatial distribution of the Twitter data that were collected during the 2014 TIFF event that occurs in Toronto. For the spatial temporal outliers, and we can see from this figure, the red ones are the outliers that were detected in the greater Toronto area. And from the by analyzing the content, here is an example. And from the topic and the word distribution, we may find this event is very closely related to the Toronto TIFF event. Then we cluster the detected events into event clusters to better estimate the event location and time. And to evaluate the performance of our proposed method, we compare the detection results with the official schedule of TIFF. So here are the results, and we can see we may the research can reach around 90% of accuracy. We further did a comparison experiment with the existing studies, and it shows the accuracy can be improved around 24%. The second type is about the traffic event detection. Before we did the research, we made an assumption that an actual traffic event occurs if a group of traffic-related tweets are found spatial-temporally concentrated. So we first do a keyword query using the traffic-related keywords, and here are a sample of them. Before we analyze their content, we did a pre-processing using the natural language processing tools by removing the stop words and stemming to their original format. Then the association rules between the tweets is plotted using this machine learning program algorithm, and from this algorithm, we further analyzed the spatial temporal features of the associated tweets. And to do a comparison, we also did a classification-based approach by involving the widely used classification methods like naive Bayes, SVM, and logistic regression methods. Similar to the social event detection, we also used the Twitter data that were collected in Toronto between 2014 and 2015. And the association rules between the tweets were mined, and here are the process of determining the thresholds. As a result, a total of 361 clusters were grouped by manning their spatial temporal features, and these clusters were identified as the traffic events. Here is a spatial temporal distribution of the spatial cluster, namely the detected traffic events. To make it clear, we made a spatial distribution and a temporal distribution respectively. Here is an example showing the content of clusters, and from the keywords and their probability, it's very clear that this group of tweets refers to a real-world traffic event. And for the comparison experiment, we compare the cluster-based method with the classification method, and here the. And to evaluate the performance, we compare the detection results with the travel speed data that we obtained from the Ministry of Ontario, Canada. So in conclusion, the spatial temporal and the semantic integrated approach can help improve the event detection rate. And these data-driven researches can help promote the development of smart cities. In the future, we may extend the detection workflow to accommodate multiple types of spatial temporal urban events. And multiple sources of social media data can be integrated to improve the detection accuracy. The sentiment analysis and the social net analysis can also be added to monitor the event progress or event evolution. because we only use the machine learning methods in the past studies. So deep learning methods can be tested in the future. So that's all my presentation about the situational awareness research in smart cities. Thanks again, thanks ISPRS and BOCA again for organizing this event. Thank you.
Thank you, Dr. Shi Shuoxu, a wonderful lecture, and which shows what is a smart city looks like and how it works, and how the geosocial media data used in the research of detecting small-scale events. And any questions? Okay, we see the student ask, by collecting information from social networks, we will be faced with a lot of fake information. What can interfere with the reliable identification of events, and how will this information be filtered?
Hello, Dr. Yeah, I think you can notice the 问答. Yeah, I think some students put their questions on this board.
Is this one or no? This one? Oh, these are the questions, right?
Yeah. Thank you.
Okay. So for thanks. Okay. For the first question, I think this question is mainly related to the data filtering or the data pre-processing. Yeah, definitely the social media data has much noise or fake information. In my research, I did a filtering by filtering the fake users, like the advertisement IDs. So I set different thresholds for this filtering process. For example, if a user keeps posting tweets in a short, maybe in 1 minute or in 1 hour, so such users were filtered before all the Twitter data go to the next process. And from other researches, the filtering such, and from my perspective, I filter such users. And from other researchers, they may focus on filtering the tweets. Like they may focus on the tweets content and use specific, like use a list of specific keywords for this filtering. So in summary, I think this information can be filtered by users or by tweets. And the second question is, okay, sure. So but I don't know how to share the PDF or a PowerPoint. Hi, Mr. Huang.
Hello.
Sure.
Hey,
Hi,
Hi.
Mr. Huang. So either anyway, because some student asks if the presentation can be shared. So I'm wondering if we have any access to for this sharing or.
Yeah, I think that maybe depends on your contents. I think maybe some PowerPoint is not suitable for sharing. Or
I'm sharing. I'm sharing the PowerPoint. Maybe called the summary research. My PhD researches. Cause I.
yeah.
For my publication.
Yeah, I think. Yeah, we will explain to students, some PPT. I think it is have some core technology and some essential contents for lecturer. So I think maybe some PPT is not so essential and not so convenient to share. So I think don't worry about it. We will explain to some related students. Okay. Okay.
Sure. Yes, Okay, I think this the third question is similar to the first one. You mean how to filter the unreliable or the fake information that were from the geosocial media data. So I may repeat briefly. In my opinion, I think this fake information can be filtered by the tweets or by the users. So you can set different rules or different thresholds for this filtering process. In China, I think the digital twin is a very hot word in recent years. And because I have a geomatics background, and in our field or in our major, here like the city information model is another like a 3D model of all the smart cities, and this model is very closely linked to the digital twin. And from our department or from our school, we create a new course for the undergraduates called City Information Model and Geoinformation Sciences. So, so in my opinion, I think the digital twin or the AI technologies can aid the development of smart cities in China. Okay, hope my answers can answer all the questions.
Yeah, okay. Thanks again for Dr. Shishuo Xu, and for this session, the time is up, and thank you for the wonderful lecture. Thank you. And tomorrow, the fifth lecture will start at 3 p.m. in Beijing time, and see you there.
Okay, everyone, see you tomorrow. And thanks again for Dr. Xu Shishuo. 谢谢徐老师。
Thanks. 谢谢黄老师。
好。
Thanks, Mr. Hong.
拜拜。
Okay, bye bye.
Bye.